We are about to embark on a field of mathematics called graph theory. There we go. And they're not the kind of graphs that you've done in other math classes where you're graphing curvy things or lines. Oh, good. Pretty good turnout today. You brought me a treat. Maybe.
Maybe? There's many numbers.
All right. So this is part of an area, a bigger area of math called discrete mathematics. And discrete here means not continuous. It means counting things. So another area of discrete math that we played with before was probability theory. We touched on it a little bit when we were doing growth models with those recursive formulas. So here, a graph is, you have these points. And then those points are connected by lines. And the lines can be straight or not. So for example, I could connect those two with a line. Maybe there's two ways to get there. So you could think of them as cities, and there's two roads that go to that city. You could think of them as houses. There's different routes to the house. There's all kinds of different applications for this kind of thing. So this is an example of a graph. Another graph might look like this. So those are different graphs. Terminology with respect to the graphs that we're going to be exploring in graph theory, and then we'll look at some actual problems. Let's see what color do I have? Blue. The blue things are formally known as edges. So you'll see the word edge a lot in the reading. And the points are formally known as vertices. Vertex is singular and vertice is plural. Okay. So vertices, me. It's the plural version. So the first graph I drew has 1, 2, 3, 4, 5 vertices. And 1, 2, 3, 4, 5, 6, 7 edges. Okay. And every graph is a little bit different. Each of these graphs has a property called connected. Which means you can get from one vertex to any other vertex. So I'll write that down on the next screen. So the graph is connected. Yeah. You can get from one vertex to any other vertex. Okay, another way to put that, there is a path from one vertex to any other. So important words here are connected, path. So a path is just a way to get from one vertex to another by following edges. And there have been a lot of different graph theory problems throughout history. It didn't get formalized until maybe a couple hundred years ago. And one of the famous problems is called the Königsberg Bridge problem, which we'll take a look at. What's up?
That does not sound like fun.
What? It's a lot of fun. So, okay, so why the heck would we bother doing this? All right. Oops. And why bother?
Why bother?
Yeah, why bother with this stuff?
Why not?
So, yeah, one answer is why not? It's fun. It's cool math. But it turns out there are a lot of applications for this. So people, institutions, groups that think this is important is the United States Postal Service. UPS thinks this is pretty important too. Any airline company, this is very important too. Companies that do
Bus routes.
large sales areas, what's that?
Bus routes.
Bus routes, yeah.
I say it differently. I don't know how to say it here.
Bus routes, whatever you want to call them, yeah, bus routes, that comes up for. If you're a company who ships a lot of stuff like Amazon, this is super important to you.
Verizon.
Can this come up with telephone stuff? Absolutely, yeah, this totally does. Yeah, cell phones.
So you're basically saying that it's used for.
Almost everything we interact with in our life, graph theory plays a part in these days, yes.
Okay.
Yeah, like how does a telephone, a cell phone, find its way from one phone to another phone?
Could you
Right.
say for another word for it?
It's
It's
gonna
like a
jump from
schedule.
one tower to
almost?
another tower, what's that?
It's like almost like a schedule.
Scheduling is involved in this,
Okay.
certainly too, yeah, so anything involving scheduling or moving stuff. Okay.
As well as one hooked together.
So it turns out this is like ubiquitous in our lives. It's all over the place. These things where we have to get from one place to another, or we have to have things happen in some kind of order. Graph theory can help us find solutions to those problems. Or say there's no current solution, we got to change the situation to make a better solution.
So with this, you could always keep that like for planning, right?
Yeah, so planning. So people that do logistics kind of work, they're totally in the graph theory. If a mailman, mailman has to deliver to every house, right? What's the best path for them to take through the roads so they hit all the houses without doing too much repeat on certain roads? UPS is a slightly different problem. They don't hit every house. They have a slightly different connection of houses, but they have some kind of plan how to go about that to waste the least time and gasoline, for example. Okay, and so those are the kind of problems we can solve with this right here. Okay, so we're going to start looking at, once we get used to the terminology and the pictures, how can we solve these problems for certain situations? And then the cool thing about this stuff, like most things in math, once you get down the basic procedures, the steps you have to follow, computers can then do bigger problems for us. We just say, here's the information, start running through this particular routine, and see what you come up with. So all of this has been computerized since its origins. All right, let's take a look at the Königsberg bridges, and then we'll do some more definitions and solve some problems. Did I ever open up my open math? I thought I did somewhere. There it is. Okay, where are the Königsberg bridges? Okay, here we go. Throw that sucker up a little bit. So a guy named Leonhard Euler, got a weird spelling, E-U-L-E-R, is one of the pioneers in this field. And, people walk for exercise. They've been doing that forever. Sometimes it's a necessity, sometimes it's just to get exercise. And so there's this town called Königsberg that has a whole bunch of bridges running through it. And so people walking around town used to try and hit every bridge on their walk if they were going for a long walk. And then someone posed the question, is it possible to walk every bridge once each and get back to where you started? Okay, so I would like you to try that. Draw this picture, the one with the North Bank Island, South Bank, East Bank. You need to blow that up for you, Micaiah. Can you see it?
No, I can sort of see it.
How's that better? So what I'd like you to do is see, is it possible to say if you start at the North Bank, to hit every bridge once and get back to the start? So I would recommend writing something down on a piece of paper.
Starting where?
You can start anywhere, but I said let's start at the North Bridge.
North Bank.
Okay. Or North Bank, thank you. North Bank.
Kind of necessity or just an exercise I do because I have no car.
All right, so I'm going to copy that into my screen here and give it a shot.
Slowly down.
They're all slowly going.
Well, so die eating mini numbers. Hey, 289 for 8, that's not bad. That's what I thought too. There's no way.
There's no way.
There's no way because there's only 3 bridges. Wait a minute.
Oops.
That's what I said last time, and he found a way.
Are you sure?
Yeah, you did. You showed us, and I was still like going at it. Weird.
Nope. Close.
Okay. So Justin had a good point. What was it again?
Only 3 bridges in the North Bank, or on the North Bank.
There's only 3 bridges on the North Bank, right? So you can't get back.
If they had 4
And
bridges.
it turns out the problem with trying to do this is, so what we're trying to do is we're trying to create a circuit here. Spell circuit is circuit. There we go. So a circuit is where you get back, you hit every vertex and get back to the starting. Well, let's see. A circuit is just making a path that goes back to the starting vertex.
That's what school was.
So a path that returns to its origin. Whereas a path is just getting from one place to another. Okay, so I can make a path from, so here I have a path from the North Bank to the East Bank. Okay, I could have made a shorter path from the North Bank to the East Bank by just doing that right there. Okay. So a path just gets you from one vertex to another. A circuit takes you back to where you started. Okay, so I didn't quite make a circuit here. Okay? I could have. There's another idea in graph theory called an Euler circuit. So let's see, new page, black. And an Euler circuit is a circuit that uses each edge exactly once each. And Euler discovered that it's only possible if every vertex has an even number of edges coming into it. So Justin's idea about 3 makes it impossible, and that one is absolutely right. So you can find an Euler circuit. Oops, wrong spelling of Euler. So each vertex has an even number of edges, then we can find an Euler circuit. And so sometimes we change the problem to make the solution we want possible. So we can do what's called Eulerizing the graph, which is to add edges so that every vertex is even. So we'll try that in a minute. So an Euler circuit is where you hit every single edge once each. It's a circuit, so you have to get back to the start. Turns out you can only do that if every vertex has an even number of edges. Okay. Another word, a little more definitions before we do some more work, is the idea of the degree of a vertex. That just means the number of edges that vertex is related to. So we'll analyze this vertex for degree, and then we'll try to Eulerize it and see if we can make a path or make an Euler circuit. So remember, circuit means I gotta get back where I started. So often we kind of abstract the picture when we're working with things like this. So the way I would normally redraw a picture of that is the north bank, I'll just call that NB right there. And then we have this island hanging out. That's a vertex. South bank is another vertex. And then over here we have the east bank. And then we can draw the vertices, which are the bridges. So north bank to island, there's 1, 2 bridges. Island to south bank, we have 1, 2 bridges. And then the east bank is connected to everything. So that would be an abstraction. The graph, that would be the actual graph for this situation labeled. And so in parentheses next to these, I'm going to write the degree of each vertex. And again, the degree is just how many edges are connected to that vertex. So for example, the north bank has 1, 2, 3 edges. So its degree is 3. The island, 1, 2, 3, 4, 5, its degree 5. East bank has degree 3. It's got 1, 2, 3 edges. And south bank is also degree 3. So everything here is odd, which means we're never going to be able to find an Euler circuit. So what we could try to do is start adding edges so that we can make that circuit possible. So let's see, everything is odd.
Which is what's the east bank?
To where? East Bank?
Yeah, east bank.
So if we did, for example, another one from East Bank to North Bank, that bumps its degree up to 4. That means that degree is 4 now, right? Okay, where else could I add one? How about the island to the South Bank? If I added another one like right down the middle there, that would make this one 6 and this one 4. So when you redraw the graph by adding extra edges like that to try and make an Euler circuit, that's called Eulerizing the graph.
Yeah.
Right? So this modified graph here is called an Eulerization. So we're going to crash course in the next couple of days. We'll just start playing around with these. So I'm going to leave this as a homework exercise. We'll revisit it on Wednesday. So has everyone got this Eulerization written down?
Euler what?
Eulerization,
Oh,
this modified graph. So your job, we're going to move on to a different problem right now, but your job between now and Wednesday is to try and find a circuit through there, an Euler circuit. Okay. Bonus, anyone that comes back on Wednesday with an Euler circuit through there. Pretty cool. Yeah.
I'm sorry, you want an Euler circuit?
So an Euler circuit means, for example, starting at the north bank, get back to the north bank using every edge once each.
Oh, boy.
Okay.
That's a bonus for Wednesday.
That's a bonus.
Okay, so we'll come back to that later. All right, let's see, what else should we look at? Okay, so we get the idea. Vertex, edge, path, circuit. Oh, I didn't go over loop yet. We'll go over weights in a moment. All right, let's do something. How about, where's my handout? Oh, Ben, I forgot to give you the handout. You didn't pipe up. Let's get that to Ben. And then we'll do an example. Drive. Math 105, graph theory, worksheets. And we'll share this with Ben.
Okay, thank you.
Yeah. Okay, it should be arriving in your drive any second. Okay, so let's see. Let's take a look at the first one on the worksheet. So we'll go through some of these. What is the degree of vertex E? What do you think? 1. There's only one vertex related to it, yeah. What about vertex A here? What would its vertex, what would its degree be? Looks like 4 edges to it.
Yeah.
Okay. So sometimes we need to be aware of the degree of a vertex. All right, next one. Is this graph connected? No, you can't get from, say, this vertex right here to that vertex right there. So it's not connected. All right, so just basic stuff. All right, so I didn't talk about Hamiltonian circuits yet, so I better talk about those. Euler was concerned about the edges. Hamilton was concerned about the vertices. So to be a Hamiltonian circuit, we want to get from one vertex back to itself and hit every other vertex once each. Okay, so Hamilton was concerned about the vertices. So let me write that down. Whereas Euler was concerned about the edges. So again, the big difference, Euler was concerned about the edges, hitting each edge once each. Hamilton was concerned about the vertices, hitting them once each. Okay, so each vertex once each. And so that's what I want to mention here. Euler, polarization, Hamilton. So let's take a look at this one, copy it. So let's see, do you think it's possible to make a Hamiltonian circuit? Let's say starting here. So a lot of times I'm going to make notes on graphs, especially when they're more complicated, about where I start. Not too bad.
Good. Very good.
So I don't have to worry about other edges. I just need to hit each vertex. Okay? So Hamilton was concerned about the vertices, each intersection. And so that would be an example of a Hamiltonian circuit. Started here and went around with that. All right, so there's an algorithm called Dijkstra's algorithm I want to look at with you, and it's a wee bit complicated. So we'll look at the wording and then we'll get the shot together. So let me bring up the wording here. Let's see, I think I want that one.
Sorry.
Are you okay? Are you multitasking?
Yes, I am.
Can you try to focus, please? That'll make me so much happier. Thank you. Ooh, this came out weird. Okay, where are you, Dijkstra? Oh, I must have passed it. There it is, Dijkstra's algorithm. Ooh, that did not come out good. Let's see if I can clean it up.
That's an interesting name.
We'll blow up the font a touch. How about that? Okay, so we get Dijkstra's algorithm here. Let's make this a bulleted list to make it easier to read. Do I have bullets? Yes, I do. Okay. So we'll go through it and then we'll give it a shot on a graph. So let's see, I want a graph to play with. One of the graphs here. I think number 3 should work. 3 is kind of easy. So which one would be good? Number 9. Oh, that's the wrong handout. So don't worry about writing that down. It's in the notes online. In the book, I mean. Let's see. So I made a note to myself to try this on number 9. Oh yeah, number 9 will work. Oh, they won't let me copy and paste from there. Really? Copy? No. Okay, we got to do a screenshot. Come on. Okay, I'll shrink that down a bit so it fits on the screen. All right, so it says to mark any ending vertex with a distance of 0. So with Dijkstra's algorithm, what we're trying to do is find the shortest path from one place to another. This graph is too short to do that, isn't it? No, we can do it. All right, and we'll do a more complicated one. So it says pick your let's see, your ending vertex, and then find all vertices leading to that vertex and calculate the end distance. So the first part is kind of like ridiculously easy. Like, why did we even write a step for that? So let's suppose I want to make the shortest path. Excuse me. From C to D. Oops, D and D not very well. From C to D. So D is my ending vertex, so I mark that with a 0. So I just come over here and I put in parentheses a 0. And then what I do is I make a note of the distance, all of the possible distances that are coming from that. So let's see, what do I have? I've got a 14 here, even though it says 14, I'm gonna write a 14. There's a 1 over here, and there's a 5 over there. So I mark the ending vertex with a 0, that's my D there. And then the second line says find all vertices leading to the current vertex, D is my current vertex, calculate the distances to their ends. So from D to C, I calculate a 14. From D to A, I calculate a 1. From D to B, I calculate a 5. Right? Since we already know the distance, so this is kind of redundant, we're not ready for this step, but since we already know the distance the current vertex is from the end, we will just require adding the most recent edge. So we'll get to that in the next step. And then don't record this distance if it's longer than a previous recorded distance. So we're not ready for that since and don't part. So we jump down here to mark the current vertex as visited. Right? So once we do the first sentence for D, we can say, okay, strike D out, we're done with it for now. Then what we do is, next part, mark the vertex with the smallest distance as current, and then repeat from there. Okay, so which one has the smallest distance heading from D? A does, okay. So A is now going to be my current one. So I am just going to circle A to be current, and so now I'm concerned about the number 1, so I'm going to put a little bracket around it. And then I repeat from this step. Okay, so I'm going to use a different color for that. So from vertex A, I can't go back to D. I'm done with D. Right? I'm just reaching out from A, from there. Let's see, I only have 2 options, right? So I can head over to C. Now, when I make my mark here, let's see, since we already know the distance, the vertex is from this end, we'll just require adding the most recent edge. So the most recent edge to A is 1. 1 plus 3 means I have a 4 getting up there to C now. Oops, I shouldn't have put that in brackets, sorry.
And then you'll have 11 if you're going to B.
Okay, yeah, if I'm going to B, I've already accumulated 1, I got a 10 to get to B, so that puts me 11 over there. All right, so am I done reaching out from A? From A, I am. Right? A has 3 vertices. D was already strucken out down here, so I could only go to C or B from there.
So you go C next. So
then what I do is I say, okay, mark the current vertex as visited, so I can strike A as being visited. So we don't need to look at that again. And then grab the smallest distance we ended up with. What's the smallest distance here? I have a 14, a 4, 11, or a 5. A 4, yeah, so this is the smallest distance. Now, oops, we stop when we get to the vertex we want. Do we have the vertex we want? Yes. Yeah, so we just found the shortest path to get there. Okay. And you say, why would I follow all those steps when I can just kind of see that that's the shortest path? If it's a bigger graph, it's harder to spot. Okay, so that's what the purpose of this algorithm is. Okay. So the shortest path from C to D would be C to A, and then A to D, and that has a length or weight of 4. So this, you have to have a weighted graph, which means each vertex is worth something. Okay. Maybe it's mileage, maybe it's time. So we want to minimize time or mileage. Maybe it's expense.
It's not that complicated.
What's that?
His brain hurts.
Brain hurts. Okay. We'll do another one. All right, get another graphic for us to play with. Let's take the one from the textbook. Where did I put that one? That one didn't come out so good. This one right here looks good. So new page, graph. Okay, so we're going to try Dijkstra's algorithm on this one. And so let's see, what were the instructions on this one? Okay, suppose we need to travel from Tacoma to Yakima. All right, so we want to use Dijkstra's algorithm for the shortest path. And we're going from Tacoma to Yakima. there we go. Tacoma to Yakima. So Dijkstra's algorithm says go to the end vertex and mark it as a 0. And then it says start calculating how to get out from that vertex. Yeah. So I could go over here to NB, that's a 103. I could go over here to MR, that's a 96. Or I could go over here to P, that's a 76. So once I've identified all of those weights to get out, I then mark the vertex I'm at as completed, and then I move on and mark the next one as current. So the next one that's going to be current is the one with the smallest weight, which would be the P. So I come over here and say, okay, you are current. So then from P, now keep in mind, we've already gone from Yakima to P, so we don't need to go back on that route. We look at all other routes from P. Okay, so let's see, we've already accumulated 76, right? So to get from P to MR, what would I have? 76 and 27?
Yeah, so we like what, 103?
103. Okay, so the rules are, and this is where it gets complicated when we have more things like that. Let's go back a page. All right. So right here, since we already know the distance to the current vertex is from its end, this will just require adding the most recent edge. Okay, so we added that on. Don't record this distance if it is longer than a previous recorded distance.
So it's not.
Okay, so let's see. We just calculated that 76 and 27 is 103, but I already have recorded a 96 for MR. So that means I don't bother writing down the 103 because it's longer than the 96. Okay. So then I move on to the next possible one. 76 plus 96 is what? 172?
Yeah.
Okay, so I write that down here. And have I exhausted all paths from P?
Yes.
Yeah, okay. So that means we mark P as done. And then we look for the smallest number on the screen, MR. That would be MR. So now we mark MR as current. And then we proceed from MR. Well, that's not bad. From MR, I have, let's see, what?
100.
I'm at 96 plus 79. What is that again? It's
103.
no, I'm at MR,
Yeah.
right? So I'm done with P. At plus 96 plus 79 is 175.
75.
Okay, so that puts A here at 175. Okay, MR has no other roots, so I mark it as. Okay, so then I move to the next smallest number on the screen, which is NB 104.
Can you do that?
Okay, so I need to get out of NB. Now we can't go back to Yakima, so we have to go forward. So 104 plus 36 is what?
Wait, isn't NV connected with MR or is it not?
It's not.
140.
It's 140. Okay, 140 is smaller than 175, so we cross out the 175 and we write a 140 up there. Okay, so that's the only route for NB, so I strike out NB. All right, next smallest route number is what, the 140? Okay, so from the 140, let's see, from A, that's my current one, I could either go back to MR, because I haven't done that route yet, but that adds up to too much, so that's out. Or I could go forward to Tacoma. 140 plus 20 is 160, and that's the only route possible, so I mark that as done. I forget to mark that as current, and that is the smallest number, and it makes me reach my destination. So we've just identified that right there as the shortest route. Okay. So we're going to keep looping through that step, looking at the smallest number we've written down each time. to figure out how to get there. So let's look back at the rules again. Highlight some important parts. All right, so we know we have to start with the ending vertex marked as a 0. So then once we get that, we find all vertices leading to the current vertex, right? And we calculate their distances. So all vertices, current vertex, and we calculate their distances. Okay, and we've got to write them down. That's important. You got to make a note of it. Now, once we get past the first step is where we jump to that one. So after we've done our ending, then the second sentence comes into importance. So since we already know the distance to the current vertex, this will just require adding the most recent edge. Okay. So going back to my picture over here, when I was at MR, the most recent edge was the one that led to the 96. All right, and then we don't record the distance if it happens to be longer than something we already wrote down there. Okay, so we have to make a choice each time. Then we mark as visited, and then we move on. And then we keep doing that for every vertex that has a low value that I can pick that's not already visited. Okay, so we got to strike them out along the way. We got to note our numbers. So it's not a very long algorithm, but it is complicated because we've got this looping thing going on. That we have to keep repeating that step over and over until we're done. So that does hurt one's brain a little bit, but it's something we can program a computer to do. So just to note, where is that? That exact problem we just did, ooh, that was weird, is, ooh, interesting. Google does not like this document. Let's look at the PDF version. Let's see, where's the PDF version? Oops, where's my open math? There it is. Shrink that down a touch. So in the book, they list Dijkstra's algorithm, and they do that problem right there. So right, they're trying to find the shortest path to get from Tacoma to Yakima. And so step by step, they go through marking the things like we did, trying to find that shortest path. Okay. And then they end up with that 160 that we did. Okay. So we'll try another one of those next class. Let's see, what else did I want to look at today? We'll do one more, and that'll be good. And went over an Euler circuit. Let's see, what do we have on the worksheet to look at? Worksheet. All right. So 9 actually asked a different question. I just wanted to use its graph. So we did 1, we did 2, we did 3. Okay, draw the circuit produced using the nearest neighbor algorithm. Okay, let's take a look at the nearest neighbor algorithm. So I'll grab, oh, interesting. Why is that happening? Oh boy, that was strange. All right, nearest neighbor algorithm. Let's blow it up a little bit. 24 should be big enough, I think. Maybe not. Let's go 28. Oh, I didn't do anything. Okay. And will let me do numbers? No, only bullets. Okay. All right. So with the nearest neighbor algorithm, we select a starting point, and then we move to the nearest unvisited vertex, the edge with the smallest weight. And we repeat this until the circuit is complete. Okay, let's see. Let's grab that picture. Do I have it available right there? Oops, wrong one. This one right here. And one thing to pay attention, there's details in the problems. You got to online, you got to pay attention to the way it says it. I'll do an online one in a minute. This one says start with the vertex on the far right. Okay. So we're going to start. Oops. With a pen. There we go. At this one here. That's right, isn't it? Yes, that's right. Okay. So what we do is we move to the nearest unvisited vertex with the smallest weight. Well, that would be this one right here. And then from there, and we're moving in this direction, we're trying to make a circuit. So then from there, let's see, who has the next lowest weight? Actually, I should label these. Do they come with labels? No. Oops. What are they supposed to?
Oh, okay, B, C.
My labels are missing. Let's see what the homework ones look like.
This theory.
Yours have them? Oh, yours have them on them?
Yeah.
Oh, does number 4 though?
That's like number 7, but it's the same.
What about number 4?
No, number 4 doesn't have it.
Oh, okay, that's right, because we're actually, in the problem, we're actually supposed to draw it out, so they're not labeled. So I'm going to label these guys based on the labeling for number 7. So how did number 7 do it? 7 started with A and goes around counterclockwise. All right. Okay, so we'll call this one A, and this one B, and this one C, this one D, and this one E. Okay, so next we should move to what? C as the next lowest weight. Okay. And then from C, we want to go,
10.
well, unvisited. So I can't do 5 because it's already visited.
10.
All right, so 10. Yep, I have either 15 or 10, so it's got to be 10. And then,
8.
let's see. Yeah, it's got to be 8 because if I try the 7, A is already visited, right? Because it has to be an unvisited one, so I have to go to 8. And then here, I want to get back where I started, so I have to go over there. Okay? So the way we write down a circuit is list the letters in order. So our circuit here would be A, B, C, D, E, A, because I'm making a circuit, I have to end where I started. So that's how I would describe the circuit to somebody. All right, let's do it again. Nearest neighbor is a little easier than Dijkstra's algorithm. Yeah. So Dijkstra's algorithm was for a path, by the way. Right? This is for a circuit. So algorithm depends on what we're trying to accomplish.
Seems circuits are a lot easier than that.
All right. Oh, and by the way, how much did this circuit cost us? We didn't actually show that. Let's see, we got 1 plus 3 is 4, plus 10 is 14, 8 is what, 22, and 11 is 33.
8.
Okay, so this particular circuit cost us 33, whatever, time, miles, dollars. Okay. Do it again, and then I think that'll be enough, and you guys can go play on the homework. I'm going to copy that, and we're going to do it again. But we're going to start at a different vertex. So let's label them. Same way as before, A, B, C, D, and E. This time we are going to start at C. Okay, so you give it a shot. use the nearest neighbor algorithm.
That can do counterclockwise on this one or not? Or do you want to go clockwise?
Well, you can, the nearest neighbor algorithm says, once you pick your starting point, choose the smallest path or vertex, smallest edge that isn't already visited, right? So what would be my starting point here? Would I go to B, A, E, or B? B's got the shortest one, yeah. Okay, so you guys continue from there. That's what has to start. Nearest neighbor algorithm. Okay. Should have done that. All right, so I think I got C, B, A, D, E, C. Anyone else get that?
Yep.
Okay. So let me just redraw that. Let's see. Those guys. I'll draw a pilot here.
Whoa, that's pretty awesome.
Oh.
Does it work for you?
Let's use a highlight here. Okay. So I went C to B first because 3 was the shortest path coming out. From there, you can't beat 1. Right? So you got to pick the 1 to A. Okay, so from there, I could either go to C, D, or E. C's already visited, so I can't use that one. But D is the shortest one, 7 or 11. So I picked the 7. Now, from here, I have to pick the nearest unvisited vertex. Well, E is my only choice at that. And then from E, I have to make a circuit, so I have to go back to C from there. So usually your last 2 are dictated for you. You don't have much of a choice after that. So starting at C, that's my path. So C, B, A, D, E, C. Okay. What's that path or that circuit worth here? So add up the numbers that we used. Is it the same as last time or different? It's the same graph. I just started in a different spot.
Yeah, about the same, yeah.
I get 45.
I got
30.
30.
So
Three,
that's
that's
4.
four.
3, 1 is 4, 11, 19.
33.
Oh,
You
I
didn't
have
go to
11.
11.
What am I doing? Why did I have another 11? What's the answer?
33.
33? No? 34? 34. Okay, we got more 34s. Okay, so this one was 34. Previous one was 33. It was better. Okay, so if you get a different result depending on where you start, how do you know where to start? Well, it could be you have to start at a certain place because that's your home base. But it could be you could start anywhere. In which case, to find the answer, you have to repeat the nearest neighbor algorithm for every vertex. So fortunately, there's only 5 here. So we can do this. So let's split up the work. So what have we done so far? So far, we've done A and C. Okay, so then for B, we'll have Madeline and Julia do B. And then for D, we'll have Micaiah and Adri. And then for E, we'll have AJ and Justin. And then you and I can do whatever we want.
Wow.
So pick another vertex to start at. So let me get a blank version of this. Let's copy that. Control C to a new screen. Okay, so here's our starting point. So you can sit down and work together, or work it out separately and compare notes.
Oh, yeah.
Okay, Adri. Hey, what are we doing?
Starting at B.
So.
I went to A.
Yeah.
And then I went to B.
Tacos over.
Oh, no. Yeah.
89. For 8 of them, I'm not gonna complain.
So, B.
Oh, the cost.
Did you guys get a weight on that?
Yeah, we're at 34.
For E?
Ouch.
That's 8, but I didn't do DDE, which is 8.
Yeah. So we have B to A and B to D. And then D to E, or not E to D.
All right, you guys got, which one did you do?
The B, start with
B?
B.
Okay, and what was your weight?
34.
34, okay.
That one. Does that have it coming on?
How's D going? You were B?
Yeah.
Oh, you guys B or D?
Oh,
I thought I said D.
They did,
Did
yeah.
I
We
give you
did
both
B.
B? Okay, well, I'll do D then. Since I forgot.
Yeah.
All right, did you guys get 34 too for B?
yes.
You got 34 also? Okay, so let's see, I didn't do D yet. So starting at D, I should go to what, A? Good. And then to B, and then C, and then I have to go E, and then back to D. Okay, so that was starting at D at 34, right? Somebody double check my math there. I was thinking 7 and 8 is 15, plus 15 is 30. 34. Plus 4 is 34. Okay, so so this algorithm is, it doesn't matter where you start, you just need to find the shortest Hamiltonian circuit, right? Because did I hit every edge? No, I hit every vertex. So if you hit every vertex, it's called a Hamiltonian circuit. If you hit every edge, it's called a Euler circuit. So this was a Hamilton circuit. And according to the repeated nearest neighbor algorithm, which is a lot of work, right? Because you got to do it once for every single vertex, we find starting at A gives us the minimum cost for this. Oh, that was exciting. Okay, so fortunately and unfortunately, we have like 3 more algorithms to go over. So I'm going to stop here. We'll do those tomorrow, Wednesday. And then we don't have class on Friday because of our Thanksgiving break. So I'll extend the homework out through Monday nights. So that way we can wrap up any problems people have on following Monday. Okay. And then there are no new chapters. The week after is the last week of classes. There's no new chapters. It's just getting ready for the final, tying up anything that people are missing. All right. So we're almost done. So take the rest of this 20, 25 minutes and take a look at the online homework. You got to read the directions carefully. And otherwise, if you like don't read them all carefully, then the problem won't work out well for you. Because some of them are a little bit tricky in terms of how you interact with the computer. All right, so hop on a computer. Ben, how you doing out there?
Good. I have a question.
Yep.
If we start from the B, and also we start from B and then to A, and
Yep.
then to D,
Yep.
then after that, can we just directly go to B, or why we have to go to E first?
So the nearest neighbor algorithm says you have to go to the nearest unvisited vertex. So let me put this on a new screen. Okay, 1 sec. So if I start at where? B? Is that what you said?
Today will be a great day.
Start at
Today
B?
will be a great day. We got the worst news ever. Oh, the prices died 2 years ago.
Then which vertex did you want me to start at?
From the
Make you fatty a little bit, so.
B?
No. All of it.
So if I start at vertex B, I have to go to A because that's the cheapest route.
Mhm.
Cheapest route from A would be D. And then from here, I have to go to the nearest unvisited one. Now, so that means I have to go to E next. Because E is cheaper. And then I have to go to C because it's the only unvisited one. And then finally, I can get back to B. So that would be the route from B.
all right.
So this is where I started. And so often I'll put arrows on my path showing how the direction I followed also. But it's the nearest unvisited neighbor is the catch.
Oh, okay, got it. Thank
All
you.
right. Cool. All right, have fun and email me or message me if you have any trouble with the homework.
Yeah, I will. And
Okay.
also, for my written assignment, for I think it's for the statistics
Yep.
chapter, my writing assignment, the score is not. I think it's not right yet. Because-
Okay, I will make a note and take a look at it.
Okay.
So statistics.
Mm-hmm.
Okay.
Statistical or property, I'm not sure. last one. because-
Okay, I'll look at them both.
Uh-huh. Right.
Okay. All right, thanks.
Thank you. Have a
Yeah.
great day.
You
Bye.
too. Bye-bye.